right? So top part, concrete in compression, fine, no problem. But when concrete is in tension, it's too weak. We just ignore it, right? Assuming the concrete is not there. 當咗佢冇到嘅。Okay? So below the neutral axis, only the tension reinforcements are there, assuming. Okay? So the tension, the reinforcement, of course, are in tension. So if you look at in practice, the reinforcement cage, the bottom bars are the main bars. Bars means reinforcement. So the main bars are at the bottom. And then you've got some vertical links. Those are shear links. We won't be able to talk about this time. We'll cover this next week. But then you can also see the top reinforcement. At the top, you also have some reinforcement in practice. Why? That's not because of bending. Nothing to do with bending. What are those reinforcements? Those top bars. Why are they there? It's nothing to do with bending. Because we know when it bends, that's sagging, and the top is in compression, there's no tension. We don't need reinforcement to take tension at the top, but you still put it there. Why is that? Why we need to put those bars? Looks like redundant, 好似多餘. No, it's not 多餘. Remember how you construct a reinforced concrete beam? 你做咗個 formwork 先. You set up the formwork, you put the reinforcement cage, 紮鐵, and then you pour the concrete, you cast your concrete, and then what's the next step? What's the next step? What's the next step? 落咗咯，落咗點？ You let it harden. 石屎要等嘅，你唔係摸咗落去就算咯。You let it harden. And during the hardening, what happened to the concrete? That's something you should have done it in your material part. What happened to the concrete when it hardens? Two things happening. Of course, there's a lot of chemical reaction undergoing. So what happened when the concrete hardens? Two major things. First, heat release. 有熱能產生. That's something you should know. When it hardens, heat released. Right, when concrete hardens, or the hardening stage, the heat will release. What does heat release mean? Heat release means 有熱產生，熱產生點意思? Temperature change. There will be temperature changes. So what? 溫度改變, something we mentioned before back in week 8 or week 9. Why we need to consider temperature in our structure? Because when temperature change, 熱脹冷縮, that thing will change, the shape will change actually. That's the first thing. The second thing, when it hardens, shrinkage. 水會流失㗎嘛，收水嘛，俗稱 shrinkage. Those two things are happening at the same time during the hardening stage. If you don't put reinforcement there, what happens is when the temperature change due to the heat release and the shrinkage, when these two things happen, there will be tension developed at the top surface, actually at all surfaces. So to protect the top surface from cracking, when there is tension, there will be cracking. You must put reinforcement there, right? Otherwise, when the hardening is done, it cracks everywhere. Okay, so the top bars are not for bending purpose. It's for to avoid thermal, that means heat, or shrinkage, cracks. You need to avoid temperature change, heat release, thermal, and shrinkage, cracks on the top surface. That's why you put those top bars there. Okay? And the bottom bars, of course, it serves both purposes, for bending and for thermal and shrinkage. Okay? So that's what I want to cover on this page. That's simple enough, right? By the way, the deflector shape. And also, always bear in mind, when you try to sketch the deflected shape of the beam, those 2 points at the supports, they must be always in contact with your beam. Okay? So if you try to simplify your diagram, this one, so it would be something like this. Right? So when you draw your dotted line, make sure the dotted line is always there and there, in contact with the support. This is a curve, of course. Second. And deflected shape, right? That's the word to describe this deflection. But to be more accurate, you can actually measure the deflection. So what do we mean by deflection? Originally, the line is there. And once it bends, it deflects. This is the deflection. From the original position to the final position. This is called the deflection. So my deflection at, let's say this is my point A, right? So this is my deflection at A. I can also measure the deflection at B. Can I measure the deflection at B? Yes, of course, why not? Can I measure the deflection at point C? Yes. Can I measure the deflection at point D? Yes. So this is my deflection at A, this is my deflection at B, at C, at D, wherever you like. But you should notice, they are not the same. The deflection values at different points keep changing. Definitely they are not the same. What about the deflection at the supports? 0. There is no deflection at those 2 supports. Right? They're in contact with the beam. So there's no deflection there. But then at all other places, they keep changing. They're not the same. Okay. Then the next example is, let's skip the next slide first and then come to the second example. Right, this one is a bit more complicated. You got a beam continuous 連續嘅. It's 2 span, 兩個跨度. So this is my left span. This is my right span. And I got 3 supports, A, B, and C. It's continuous. 2 span, continuous. So the picture below it, right, just give you an example or an idea of a 2 span. actually this one is more than 2 span. Right? 3 supports. 1, 2, 3. This beam, of course, or this bridge is actually more than 2 span. Now, the same thing, we try to sketch the deflected shape of the span. So to do this, we try to simplify this thing a little bit. Put it here. Okay, I got 3 supports, the left, the right, and the center. And what is my loading? It's a uniformly distributed beam, 1 fan ball, on the whole beam. So it's, remember the symbol? We'll talk about this in week 8. This symbol represents distributed load. That's just a symbol to represent this uniformly distributed load. So the main thing, of course, is not these terms, it's how you sketch the deflected shape. So common sense will tell you, if you got loading here, of course, it will push down. Same thing for the right span, it will push down. So you expect the beam will 左邊窩咗落去，右邊又窩咗落去。Right? But then bear in mind, there's a support at the center. So what does that mean? The beam must always be in contact at those supports. So it goes down, the beam 喺度窩咗落去，呢度又窩咗落去。But it should also go up here. So the beam should go down, but then it should go up, and then go down again, and then go up. That's how the beam should deflect. A smooth curve. 一條順滑嘅曲線 that pass through this point, that point, and that point. So to draw it's so try to practice on your paper. It goes down, and then it goes up. Bear in mind it's a very smooth curve. So make sure that when you draw, it's a smooth, curved, dotted line. Right, so 窩咗落去，夾咗上嚟，窩咗落去，就畫上嚟。Now, the next step is you need to tell yourself, or you need to ask yourself, which part is sacking, which part is hawking. So obviously the left part here, it 窩咗落去. But then if you look at the center part here, this part here, that part here, 佢夾返上嚟. So it goes up again. That's hawking. But then it goes down again. So that part is sacking. So this beam has 3 different parts. It sacks, and then it hawks, and then sacks again. So I can divide this into 3 parts. Let's say here, about there. So this part, that part, 3 parts. Sack, 窩咗落去，彎返上去 hawk， 又窩咗落去。Now, so from the deflected shape, you can tell which part approximately it's sacking, which part is hawking, which part is sacking. So this beam has actually 3 parts, sack, hawk, sack. So from sacking, I can tell this part of the beam is sacking. So that means you now look at these 2 diagrams together. This part is sagging. This part. This is sagging. Right? And then this part, hog, H-O-G, hogging. And it goes to the right part. This part is water sagging again. Right? So the two are actually they're the same diagram, except that on the right I just try to simplify it a bit. So from the sagging, what can you tell? Sagging means the top part is in compression. You can see the color difference. Top part is C, bottom part is T, tension. But here you have hogging, this center part here. So compression and tension side, it flips. So this becomes T, you can see the color change. Right? And then when it goes to the right, your water. So C and T flips back again. So this is C, and this is T again. So if I ask you if this is a reinforced concrete beam, you should be able to tell me where to put the main reinforcement. Where are the main reinforcement? So it should be here in the tension part. Then it goes to the top. Then it comes down again. Those should be the place where you have main reinforcement. And for the remaining parts, you should also put reinforcement for thermal and shrinkage control. Right? So this is how you can actually identify which part of the reinforcement are main reinforcement, which part are not main reinforcement. Okay, so okay, another one. The third example is on the next slide. It's a very typical cantilever. 應該聽過呢個字嘅，懸臂。這個寫嚇，懸臂式嘅結構。Very typical example is the cantilever beam supporting this balcony. You can look at the picture below. Right, that's your cantilever beam, that one. And where's the support? This end, it's fixed to a wall. So this is where your beam is supported. So this beam is supporting the load from the balcony above it, right? So supporting this balcony here. So you got this cantilever beam, this support. This end is the free end. This end here, that's a free end. F-R-E-E, free end. Free means it's free from any, there's no support there. It's free of any support. There's no support. So it's called a free end. So if you try to simplify this diagram, that's what you have. So you have a beam supported at this end. That's the free end. That's the support end. S-S-U-P-P-O-R-T. And you got some load on the beam. Right? So it's something like having a beam like this. got loading coming from the balcony above. You got loading on the beam because it's supporting the balcony above. And at this free end, there's nothing here. Nothing happens there. So what do I mean by nothing? So at this free end, there's no bending. There's no bending moment. It's free from anything. It's nothing. So it's free. That's why it's called free. Right? So the bending moment is zero there. In other words, because there's no bending moment at this point, so the top surface or bottom surface, there's no tension or compression. There's nothing. It's free. It's completely free end. But if you say, what about a little bit inside? No, that is not free. Right? So free end only refers to exactly this free end. Just like, where's my beam? That's my beam. This is my free end. Only this position. That's free from anything. Okay? So, same thing. You try to practice how does it deflect if you got load, right? If you got beam like this and you try to put load on it, how does it deflect? It deflects like this. So can you tell, is it sacking or hawking? Obviously it's hawking, right? You should try to get used to look at it, right? So you put loading, so it bends like this. So this is hawking, right? Sacking is something like that. That's hawking. Okay? So if I sketch my deflector shape, it's actually on your handout, that dotted line there. It's your deflector shape. Obviously it's in hawking. So what does that imply? If it is in hawking, that means the top surface is in tension. That's where you should put your main bars. Bottom side is compression zone. The bottom half is in compression. So you don't need reinforcement for bending. But you do need reinforcement for other purposes. That bottom bars, again are for thermal and shrinkage cracks. This one. Of course, you also got shear links, but those shear links we won't cover today. We'll do it next week. Okay. Now there's a slide that we skipped 5 minutes ago. This one. This is just a schematic. It's not a real picture or a photo or a diagram. This is just a schematic. 示式嘅圖像. Just trying to emphasize crack and tension. Remember this beam, of course, just looking at it, you know this is in sacking. So where's the tension? Tension is at the bottom. Right? So with direction of the tension, remember, that's the direction of tension. So if I indicate, if I tell you, or if you are given the direction of the tension, can you draw me the crack lines? Remember, when the concrete is in tension, it cracks. Right? So what did we say at the start of the lecture? Remember what we said at the start of the lecture? If you have a piece of concrete, if you try to apply tension, pull like that, then you will see crack lines. The cracks are perpendicular to the direction of tension. if you have a beam, like that, with tension like that, so those are the cracks. You see the cracks are perpendicular. Of course, it's a bit exaggerated. Don't you go crack on foot. Right? So all these cracks are perpendicular to the direction of the tension. You see the words here, vertical cracks develop. You can underline it. Why vertical? Because the tension is horizontal, that's why. Okay, so the tension is horizontal. Little figure B we won't cover today because it deals with shear, so we'll come back to this next time. Yeah, so this indicates a beam supported by columns at both ends. Just lay the beam there. Okay. Right, so we've done a few examples here. Right, I won't carry on with there are just one or two more slides for bending, and then we come to shear. So we will cover these remaining few slides next time. So I guess it's time to do the in-class exercise. So make sure your phone